that would also send a message that okay. It's limited. It's 13. This is their number.
Yeah, what very difficult. Sometimes I will take the figures as a devices to be the constant material data. The people who are friend having laptops. They don't share the same device just to see the data. So that's not an absolute change. One day, no one knew. So it's not an absolute change.
Good morning, class. Today, we are starting with a new topic, which you have before you, electrochemistry. This being the first lecture, let me start by introducing myself. I am Kayode Sanusi, a professor of chemistry in the Department of Chemistry of Obafemi Awolowo University. To start, I've provided some relevant text that will be useful to have more understanding of electrochemistry. You can visit the university library to check P.W. Atkins, J.H. Noggle, L.M. Raff, K.J. Lidler, and J.H. Meza. These are good physical chemistry textbook that will give you more insight into the topic we're about to discuss. I've also provided the outline of the topic, as you can see in the lecture notes. We will start with defining the Ohm's law. And this can be done very easily by assuming a very simple electric circuit, which we have before us. If you have a source of energy, which generally we refer to as the battery, connected to a metallic conductor, and a small load, which is represented with this blue brick with a resistance R. By Ohm's law definition, it says that the energy of the electromotive force is directly proportional to the current that is flowing through the metallic conductor. Voltage directly proportional to the current that is flowing through the metallic conductor. By convention, whenever you see a tail that is longer than the other, that represents the positive terminal of the battery, and the shorter tail represents the negative terminal of the battery. Okay, so if the voltage or the electromotive force is directly proportional to the current passing through the metallic conductor, introducing an equality sign, we bring in a proportionality constant, which then makes the equation to be E equals Ri, or E equals IR. The R that we have there is now the proportionality constant known as the resistance. What this equation is telling us is that the energy stored in the battery will determine the amount of current that will flow in the external circuit. And this simple equation is known as the Ohm's law. What is current itself? Current is the rate of flow of charge Q, Q measured in coulomb. And this is the mathematical representation of that definition. That is Q over the time. Anything that talks about rate is usually with respect to time. The rate of flow of charge is the definition of current. The electromotive force E is also called the electrical potential or the voltage. And the work required to move a charge through an electric potential is given as Q, the charge, multiplied by the voltage. If you are moving a charge from point 1 to point 2, the work, the electrical work that will be required to move the charge Q from point 1 to point 2 is given by the product of the charge and the voltage across the 2 points. The voltage across the 2 points. And that is what we have as equation 2. You need to note the unit for this measurement. You will notice that the unit for the charge is coulomb and that of voltage is volt. So you can have the work done or the electrical work as coulomb volt or volt coulomb, which is equivalent to joule. Work done, any work done is measured in joule, but because it's an electrical work, we can also have the unit as volt coulomb or coulomb volt. Power, electrical power in watts is given by the product of the charge and voltage per time. That is the coulomb Q, the charge Q, multiplied by the voltage E over time. You have the unit in joules per second. You will recall that we have defined the charge as a function of the current and time from equation 1. Okay, so if you put, instead of Q, you put IT, voltage, over T, you end up having your power in as a product of current and voltage, ampere volt. The T cancel each other. So you end up having power as a product of current and voltage. These are elementary information in electricity. And we are doing this as a way of revision. So the ratio of the EMF to the current flowing through any metallic conductor is called the resistance, measured in ohm. Okay, so we have already defined the Ohm's law as E equals IR. So the resistance measured in ohm is given as E over I, which is volt per ampere. The reciprocal of the resistance is called the conductance, which has the symbol L, and the unit is Siemens. S. The unit is Siemens, which has a symbol S. And when we say the conductance is the reciprocal of the resistance, we mean it is defined as 1 over R, which makes the unit per ohm or ampere volt, because the reciprocal of the resistance is also equals to current over voltage, which will give you ampere per volt. The transport of electricity through a metallic conductor is by motion of electrons. If we go back to the electric circuit in the first slide, there is no way you can have current flowing through this metallic conductor without having a corresponding flow of electron in the opposite direction. As the current flows in one direction, electron flows concurrently in the opposite direction with the same magnitude. The magnitude of the charge being carried by one is equivalent to 1.6, approximately 1.602 times 10 raised power minus 19 coulomb. 10 raised power minus 19 coulomb. That is for electron. And for the current, which is a positive charge, okay, is the same magnitude but opposite sign, plus 1.602 times 10 raised power minus 19 coulomb. And that is exactly what we are talking about here. The transport of electricity through a metallic conductor is by motion of electrons, each of which carries a charge minus E, with E equals to 1.602177 times 10 raised power minus 19 coulomb. If there is no flow of electron, there can't be flow of current. So the flow of current, which is passage of electricity, is the movement of a positive charge in an opposite direction to the flow of electron. This is exactly what I have just explained. And to further describe this, we have this diagram. I'm not sure if this is well rendered over there, but what the blue arrow is talking about is the positive current, which is the positive charge, 1.602 times 10 raised power minus 9. To have a passage of 1 coulomb of electricity, and that is what we have done here. Okay, 1 mole of electron is equivalent to 6.02 times 10 raised power 23. Okay, electron, 1 mole, okay, of electron, we have this amount of electron, this number of electron, okay, and it will carry a charge that is equivalent to 96, approximately 96,500 coulomb. But what we have here is 96,485 coulomb. But for convenience, we will be using 96,500 coulomb. Okay, so one coulomb of electricity will transport this amount of electrons over 96,485 coulomb, which will give us this number of electrons. To have a passage of 1 coulomb of electron, this number of electrons must be involved. To have a passage of 1 coulomb of electricity, rather, this number of electrons must be involved. And this is in metallic conductor. How do we have electricity in solution? The transport of charge through a solution is by ions, okay, ions and electrons. okay, each of which carries a charge that is an integer multiple of the electronic charge. For example, if you have a solution of sodium chloride, okay, in that solution, you expect to have sodium ion plus chloride ion. All right. Each of these ions carries a charge, and it is an integer multiple of the electronic charge. So equation 12 is telling us the magnitude of the charge. Okay. So 1 mole of sodium ion, okay, has a valence of 1, okay, and that multiplied by Avogadro's number n, 6.02 times 10 raised power 23, multiplied by the electronic charge, which is 1.602 times 10 raised power minus 19. And this is exactly what gives us the quantity of electricity that is expected for 1 mole of an ion. So from equation 12, we can see the definition of the parameters, where n is the Avogadro's number. The quantity Ne from equation 12 is the value of 1 mole of unit charges. That is, when the Zi is 1. For example, in the case of sodium ion, okay, the valence of the charge is 1 for sodium ion. And generally, when we say we have 1 mole, and that is called Faraday's constant, gives us Faraday's constant. So Qi equals F equals Ne. If you multiply your Avogadro's number and your electronic charge, which is 1.602 times 10 raised power minus 19 coulomb, the amount of electricity that is expected to be carried by 1 mole of ion will be equal to 96,485 coulomb per mole, equation 13. So this Faraday's constant, 96,485 coulomb, will be rounded up to 96,500 coulomb per mole in subsequent discussion for convenience. Now, before we talk about Faraday's laws, we need to understand that Faraday's laws are applicable to what we call electrolytic cell. Electrolytic cell. In electrolytic cell, you have two electrodes deep inside the solution. The solution is the electrolyte. In this case, we can say our solution is dilute H2SO4. One of the electrodes is going to be positive electrode. The other one is going to be negative electrode. The positive electrode in electrolytic cell is referred to as the anode, while the negative electrode in electrolytic cell, emphasis on electrolytic cell, while the negative electrode is referred to as the cathode. So the electrolyte will produce ions, and in this case, we are going to have hydrogen ion and sulfate ion. We are also going to have hydroxide ion because you have water, okay? The dilute H2SO4 is prepared with water in abundance, okay? Now, what is expected is that positive ions we migrate towards, in solution, we migrate towards the cathode, which is the negative electrode. While negative ions that are in the solution, we migrate towards the anode, which is the positive electrode. Now, before we go further, we need to state clearly what properties are expected for our electrodes. Okay, this is about 20 minutes into the lecture. I would like to give you the attendance code. This is the first attendance code. First attendance code. F K P U E. Again, F K P U E. F for fish, K for kettle, P for Paul, U for umbrella, E for egg. So in continuation, electrodes in electrolytic cell should have the following properties. Number one, this is not part of the lecture note. I expect you to have your pen and paper with you to make some jottings. Number one, the electrodes have to be inert, especially if the electrolyte is acid. For example, as we have here, our electrolyte is A2SO4. This is an acid. So you are using an electrode that must be inert. A very good example of inert electrodes is the platinum. However, platinum is very expensive. So a cheaper alternative is graphite. Number two property is conductivity. The material to be used as electrode must have some level of conductivity. They must be able to conduct electrons in and out of the cell. In and out of the cell. Okay? The inertness that we first mentioned is defined as the ability of the electrode to be able to withstand harsh chemical condition. They will not undergo any chemical reaction with the electrolyte. This is inertness, and this is also referred to as the stability of the electrode. So we go on. In the process of migration of ions in the solution, the negative ions will migrate towards the positive electrode, which is the anode, and get deposited on the positive electrode, while the positive ions in the solution will migrate towards the negative electrode, which is the cathode, and get deposited on the cathode. And Faraday's first law states that the mass of a substance liberated at or dissolved from an electrode during electrolysis is proportional to the quantity of electricity that is passed through the electrolyte. And this is expressed mathematically in equation 14. The mass of a substance deposited or dissolved at the electrode. Why that word dissolved is used here is that sometimes you can have a cell for the purpose of electroplating, where what you need to do is to deposit one metal on another metal to coating. And those are some of the uses of electrolysis. Okay? Dissolving. For example, if you have an electrolytic cell where you have copper sulfate as the, where you have copper sulfate as the electrolyte, you can have copper metal as one of the electrodes. You have copper sulfate as the electrolyte, you can have copper metal as one of the electrodes. Okay? In the process, the copper ion will migrate, copper ion in solution will migrate towards the negative electrode, which is the cathode, and get deposited on that electrode, coating the electrode. So the size of the cathode will increase over time, with time, while the anode, which is a copper metal, will decrease with time. Okay, because as copper ion is being removed from the solution, the copper metal, which is the anode electrode, is getting dissolved, okay, and replacing the copper ion in the solution. Okay, so that is one of the uses of electrolysis. So we go on with the first law, which is the mass deposited or dissolved at an electrode is directly proportional to the quantity of electricity that is passed through the electrolyte. Okay, mathematically that is represented in equation 14. And introducing an equality sign, we have the constant K, okay, which is defined as the electrochemical equivalent. K equals A over ZF, where A is the relative atomic mass of the material or substance that is deposited or dissolved at the electrode, over Z, which is the valence of the ion, valence number of the ion, where F is the Faraday constant. So if we go further to substitute the value of K into the equation that is underlined there, you have equation 15. So where A is relative atomic mass of an element, Z is the charge on an ion, and F is the Faraday constant, which value is 96,500 coulomb per mole. The factor A over Z without the Faraday is called the chemical equivalent. So recall that the charge Q, that is the quantity of electricity, is given as the product of the current and time according to equation 16. So we can go further to write equation 15 as equation 17 by substituting our value of K, which is A over ZF, and also our value of Q, which is IT. So we can vary the amount of electricity that is passing through the electrolyte by either varying the current, or we vary the time. Okay, if we vary the if we vary any of these two quantities, the current or the time, we are going to vary the quantity of electricity. M is equal to KQ, and KQ is dependent on current and time. So a plot of the mass deposited versus the quantity of electricity passing through the electrolyte should give us a straight line through the origin. From this equation, you can see that there is no intersect, where the slope of the graph should be equal to the electrochemical equivalent, A over ZF, the slope of the curve. Okay. Now, how did Faraday verify this first law? He set up a circuit that you have above here. You have before you this circuit was set up. B is an electrolytic cell. C is also an electrolytic cell. D is also another electrolytic cell. C and D were connected in parallel and together in series with cell B. Okay, each of these electrolytic cells contain the same electrolyte. In this example, he used H2SO4, dilute H2SO4 in each of these cells, the same molarity, that is the same concentration for the three cells. And he allowed the same magnitude of current to pass through them. Allow the same magnitude of current to pass through them. Okay, you know that if I passes through cell B, what we pass through cell C is going to be half of whatever that passed through cell B. And what we pass through cell D is also going to be half, which is I over 2. Okay? And he confirmed that because the electrolyte is H2SO4, what is expected to produce at the electrodes are hydrogen gas on the negative electrode, which is the cathode, and oxygen gas on the positive electrode, which is the anode. Okay? So these are the two substances that will be produced at the electrodes in each of these cells, in each of these electrolytic cells. And Faraday found out that the volume of the gas obtained at the electrodes in cell B is 2 times the value of the volume of the gases obtained in cell C or cell D. For example, let us assume that the volume of the gas, we are talking about one of the gases, either hydrogen or oxygen. Let us assume that the volume obtained is 5 mil in B. Faraday found out that 2.5 mil of hydrogen gas was obtained in cell C, and 2.5 mil of hydrogen gas was also obtained in cell D. So the total volume of gas for hydrogen obtained, in cell C and D, okay, is equal to the volume of hydrogen obtained in cell B. And that is exactly what Faraday discovered, which verified the first law of Faraday. So let me give you the attendance code, the second attendance code. The second attendance code. I want to believe that you are getting the concept. Sakina Adebayo, you wrote that the property of what did I mention? Okay, I was telling you the properties expected of a good electrode for electrolytic cell. In electrolytic cell, you have electrodes and you have electrolyte. What are the properties expected for a good electrode? I said the electrode must be inert, that is, it must be stable against any chemical reaction. It must be inert. It must not be able to undergo reactions with the electrolyte. And I also mentioned that it must be well conductive. It must be, the conductivity must be reasonable. It must be able to conduct electrons in and out of the cell. That is the property that I mentioned. So now I'm about to give you the second attendance code. 77 77 77 77. It's not showing. 77 5SW. Again, 77 5SW. Again, 775 SW. 775 S for sun, W for work. 775 SW. So Faraday was able to verify the first law, which says that the mass of a substance deposited or dissolved at the electrodes is proportional to the quantity of electricity that is passed through the electrolyte. The second law of Faraday states that when the same quantity of electricity is passed through the solutions of different electrolytes, the masses of the different elements obtained are in the ratio of their chemical equivalent. Okay, what this is telling us is that in this case, you have two different electrolytic cells. Electrolytic cells containing two different electrolytes. In one, maybe you have sodium chloride. In another one, maybe you have H2SO4. Okay, you have them connected in series, okay, together. All right, and then you passed a certain amount of current through them. Okay, because the electrolytes are different. Okay, the mass of the substance that will be deposited at the electrode of electrolytic cell with H2SO4 will depend on the chemical equivalent. And similarly, the mass of sodium that will be deposited on the electrode in this electrolytic cell will also depend on the chemical equivalent. What do we mean by chemical equivalent? We have said that it is the relative atomic mass over the magnitude of the charge. So the least quantity of electricity required to liberate 1 mole of an element is 96,500 coulomb, or 1 Faraday. 1 Faraday is the least quantity of electricity that you need to liberate 1 mole there is nothing like our Faraday. Our Faraday cannot get out 1 mole of an ion or an element. One Faraday cannot interface with 1 mole of an ion to get it out as an atom or as a molecule. Okay, so the least quantity you need is 1 Faraday. Okay, and for example, for 1 mole of potassium, okay, 1 mole of potassium, 1 Faraday is required to deposit 1 mole of potassium. And this is described by this first equation, because potassium has a valence charge of 1, and 1 electron will convert potassium ion to potassium element. Okay, so for an ion like potassium or sodium, you require 1 Faraday to deposit it at the electrode. Calcium, 1 Faraday will deposit half a mole of calcium. Half a mole of calcium, because calcium has 2 valence charge. Okay, it will require 2 electrons. Half a mole of calcium will be deposited by 1 mole. For you to deposit 1 mole of calcium, you will need 2 Faraday. But if you don't have up to 2 Faraday, you can only deposit half a mole of calcium. If you have just 1 Faraday, you can only deposit half a mole of calcium. But to deposit 1 mole of calcium, you will need 2 Faraday. Similarly, to deposit 1 mole of chlorine gas, you will need 2 Faraday. Whereas half a mole of chlorine gas will be deposited by 1 Faraday. To deposit 1 mole of aluminium atom, you require 3 Faraday. But if you do not have 3 Faraday, what you have is 1 Faraday. You can only deposit 1/3, 1/3 of aluminium with 1 Faraday. But for you to deposit 1 mole, you will require 3 Faraday. So the verification of the second law. The second law was verified using this setup. You have 2 different electrolytic cells, that is containing different electrolytes. So Faraday verified the second law by passing a quantity of electricity through 2 cells connected in series as shown. You can view the cell like this, and connected some of these parts are not sensitive. Okay, connected in series. You can view it. This is cell B, this is cell C. Okay, so he did that by connecting the 2 cells B and C in series, as shown in figure 2. The battery A pumps current through the electrolytic cell B to cell C. So which means the same value of current is going to pass through both the cell B and cell C. If you have 5 ampere in the circuit, 5 ampere is going to pass through cell B and also pass through cell C. Cell B contains dilute H2SO4. And the other cell, which is cell C, contains a molten lead chloride. Hydrogen is evolved in the cathode of cell B. Okay, in the cathode of cell B, which is the negative electrode, hydrogen is expected to be liberated because the electrolyte in cell B is dilute H2SO4, while lead is deposited on the cathode of cell C, because cell C, okay, contain molten lead chloride as the electrode. So the cation there, the positive ions in that electrolyte is lead 2 plus, which is expected to be deposited on the cathode of cell C. So the masses of hydrogen and lead formed were found to be in the ratio of their electrochemical equivalent. And that is what is expressed in equation 18. And we have a small example to illustrate that. But in the example, when you eventually get the PowerPoint, the slides, you will need to change this equivalent weight to relative atomic weight. For example, when 3 grams of hydrogen is liberated at the cathode of cell B, and the relative atomic weight of hydrogen and lead are 1 and 207.2 grams respectively, the mass of lead deposited at the cathode of cell C is going to be given as, okay, to deposit 1 mole of lead, you have this equation, and to deposit 1 mole of hydrogen, you have this equation. Okay, so the mass of hydrogen has been given as 3 grams, mass of lead is what we are trying to determine, and we have said that is proportional to the electrochemical equivalent. Recall that electrochemical equivalent is A over ZF. So for hydrogen, A for hydrogen over ZF for hydrogen. Then everything over A for lead over ZF for lead. So we can from here determine the mass of lead that will be deposited at the cathode of cell C, which we already have as 621.6 gram. Okay, so now let us so please, I would like to give you the third attendance code. The third attendance code. The third attendance code. G5QYY. G5QYY. Again, G5QYY. So let us try 1 or 2 examples. The first example, the mass of copper deposited during the electrolysis of copper 2 sulfate was 0.2452 grams. What quantity of electricity passed through the solution? Copper 2 will require 2 Faraday to deposit 1 mole of copper. You need 2 Faraday. Okay, so 2 Faraday, which is equivalent to 193,000 coulomb, will be required to deposit 1 mole of copper with relative atomic mass of 63.5. Okay, so what quantity of electricity is required to produce 0.245 gram? Okay, that is 0.2452 gram. That is one method. Okay, that is one method. You can also relate your equation M equals K Q. Okay, KQ. What you are being asked to determine is Q, and Q is going to be M over K. Remember, your K Your K is A over ZF. Okay, you can plug in your A, which is 63.5, and your Z is 2, your F is 96,500 coulomb. So you end up with this result, this answer, 745.25 coulomb. Another question: if 48,000 coulomb of electricity are required to discharge, change this 0.5 to 0.497. 0.497. It is not exactly 0.5. If 48,000 coulomb of electricity are required to discharge 0.497 mole of sodium from the molten sodium chloride, calculate the quantity of electricity required to discharge 2 moles. Remember, okay, your M equals A over ZF Q. A over ZF Q. Okay, and your M over A is equivalent to the number of moles. Then you have Q over ZF. Q over ZF. You have been given the number of moles that you are expected to produce, but what quantity of electricity will produce these 2 moles of lead? So only to equate this to 2, okay, your Z is going to be 2, because lead 2 plus will require 2 Faraday to deposit 1 mole of lead. Okay, so Q will then be equals to 2 times ZF. When you plug in the values, you end up with 386,000 coulombs. Let us try one more example. Then I'll leave a few minutes for questions. The volume of hydrogen liberated at STP at the cathode during an electrolytic process in 30 minutes is 1,120 cubic centimeter. What quantity of current was consumed? What quantity of current was consumed? Okay. Now, what you need to do, you are being asked to determine the value of current. What quantity of current was consumed? And you have been given the time. Okay. It means that you need to know your quantity of electricity. Q equals to IT. You are being asked to determine I without being given your Q. So you need to find your Q. How do you go about finding your Q? The volume of hydrogen liberated. So the equation that you need to write to get that is this. Okay, you need 2 Faraday to produce 1 mole at STP, to produce 1 mole of hydrogen. And the volume at STP for 1 mole is 22,400 cm3, okay, at STP. However, okay, the volume produced in that experiment at STP is 1,120. So what quantity, what quantity of electricity was required to produce 1,120? And that is this value of X that we are trying to find here, which we obtained as 9,650 coulombs. And the question goes further to ask, if 11 amperes were consumed in the liberation of 9,400 cubic centimeter oxygen at 750 millimeter of mercury and 40 degrees Celsius, what time elapsed in the course of releasing this amount of oxygen? Because of time, I'm not going to go through the solution to this other part of, I won't be able to go through the solution to this other part of the question because of time, so that I can also attend to any question from you. I want you to let me get a feedback, let me know where you are getting confused, so that we can make clarification. Any question from you? Any question? Someone is asking for my name. Said my name. Yes, I'm Dr. Kayode Sanusi, a professor of chemistry, Department of Chemistry, Obafemi Awolowo University. Any question relating to what we have just discussed? Okay, Anim BOI0112 said, when calculating, shouldn't you reduce to SI unit? Well, you do not necessarily need to go through that rigor, because at the end of the day, all the units we cancel out. For example, you are looking for volume, okay? If you have columns there, it will cancel out, okay? So, and then you get your volume, okay, in the unit that you expect to get it. You really do not need to go through the rigor of converting to SI unit. We will try and solve the other part of the second or third example that I gave. We will solve the other part of the third example in our next class. But you have the solution with you. You can also go through it. If there's any problem with it, we can revisit it in our next class. A is not molecular mass. It is wrong to say molecular mass. A is the relative atomic mass. A is the relative atomic mass of the atom or element. Queenie, where did I see the 1,120 cubic centimeter is in the question. Of course, you can get the slide. All right. Thank you very much for your attention. I will have to stop here, and then we meet until we meet again on Friday, 9 o'clock. Thank you very much.
I'm sorry about this. I didn't know it was this. So now, this is to get the reaction part. It's to get the reaction. Good morning, class. This is Professor Joshua Ojo, Department of Physics and Engineering Physics. So I'll be taking the last series of classes, topics in Physics 101. So I'll be talking about gravitation. We want to apologize if there's a little technical issue here. That's why we have not loaded the slides. But maybe I can. So we will be talking, I'll be talking about gravitation. And the gravitation is one of the 4 forces. I'm just giving them, prepping them, and listening. Yeah. So gravitation, that's what I'll be talking about. Is a very, very big issue because it's one of the fundamental forces. It's one of the fundamental forces in nature. Yes. Just delete the latter part. Please excuse me. Delete the latter part. Delete the latter part of mine. Well, you come and address them while I do that. $8,000. No.
Good morning, everyone. While we're waiting for the slide to load, I have few announcements to make. So this is Mr. Adeshope, the course secretary for Physics 101. It occurred to me that some of you are confused about the tutorial, the number of questions to be attempted. So I want to quickly clarify that. So pay attention, please. You have been given some tutorial set before. So because of those that just bought their manual, the workbook, so I'm going to give everything again. So the first chapter, irrespective of the tutorial booklet you are having. So if it is Physics 101 tutorial booklet or Physics 105, irrespective of whatever you are given, so make use of it. So you're not supposed to buy another tutorial, especially those that are taking Physics 103. So we're using that tutorial booklet for both Physics 101 and Physics 103. Okay. So the first tutorial set is the question 1 to 7. If you're giving Physics 105 tutorial booklet, if you're having Physics 101 tutorial booklet, so you have to solve question 1 to 7 of chapter 1. And if you are having a Physics 101 tutorial booklet, you have to solve question 1 to 8 of chapter 1. So for the second set, so you have to solve all questions in chapter 2 for both 101 and 105. The third set, you have to solve all questions in chapter 3. The fourth set, you have to solve all questions in chapter 4. And the last tutorial set, so you have to solve questions under gravitation. So you check question under gravitation, so solve question under gravitation only for the 5th tutorial set. Okay, and I've instructed your class rep to collect it from you. So upon completion, so kindly submit to your class rep. Please submit to your class rep. Okay, and ensure that your details are well captured, that is, are well documented by your class rep, and you sign against your name. So you sign against your name when you drop your tutorial booklet, you submit to your class rep. Ensure that your class rep writes your name, your registration number, and sign against your name. It is very, very important. Okay. So the deadline for submission to your class representative is Tuesday, 3rd of February. That's February 3rd. Okay. So you have till Tuesday to submit to your class representative, and I've instructed your class representative to bring it to my office on or before Thursday, February 5th. So make sure you submit to your class rep. Okay. So, and if you have any clarification, anything that you want me to know, you can come to my office. So my office is located at the White House Physics and Engineering Physics Department, and at the ground level, that's G14B. So you can locate G14B. So you can come and see me. Okay. Take care.
This my mom. We are life. Everything that we are sit down. This is my phone. Sit down. Sit down. You need to. Just for 2 minutes. Have you done? Have you said to me?
It's a network.
Good morning, class. Once again, I have to apologize for the itches. It's largely due to my fault. I submitted the slides late, and the network is pretty bad here, so it's not loading at all. So while they are working on it to get it uploaded, you can get talking. So like I was saying, I am teaching to address us on gravitation. Gravitation is one of the 4 fundamental forces in nature. And that's what we do in physics. We study the forces. The forces are gravitation, electromagnetic, and then within the nucleus, you have the strong nuclear force and the weak nuclear force. These are the 4 forces that are responsible for interaction. Like you know from Newton's first law, nothing happens because of inertia. Nothing happens, nothing moves. I mean, you change, you don't have any change in the inertia, no acceleration without a force coming in. So whatever the force you might think of, friction, whatever, they all boil down to 4 fundamental forces. And gravitation is one of these. It is the one that is, all 4 are always at work, but the most predominant at large distances is gravitation. At smaller distances, when you're talking about galaxies and other kind of thing, is gravitation force that is principally keeping the world together, satellites and all that. And then you're dealing with big masses. At closer distances, is the electromagnetic force that is predominant. And that is responsible for molecules and all that kind of interactions. Within atoms, within nucleus, then you have the strong and the weak nuclear forces. And these, at distances greater than a few angstroms, they become practically 0. So we are looking at gravitational forces to start with. Gravitational forces, the force of gravity, almost everybody in this class has heard about that. You know about the apple falling from the tree and Isaac Newton wondering, why did the apple come to the ground? And then he formulated the theory of gravitational forces. He did that at the age of 23, just like many of you, on his own. The big thing with gravitational forces is the equation. And I'm sure most of you are familiar with it. It has to do, the force of gravity depends on the masses involved. Every matter in life has mass. If a physical matter, if you matter physically, you must have mass, you must have charge. So it is the masses that mediate the force of gravity. Gravitational force happens between masses. So, and between each pair of masses, every pair of masses on Earth or in the universe interact. There's gravitational force between them. So the force of gravity is proportional directly to the product of the 2 masses. So F is proportional to M1 and M2. M1 times M2. You probably knew that. But it's profound, and that is, so the larger the masses, the larger the gravitational force. F is proportional to M1 and M2, and it occurs between pairs of masses. If you have 20 bodies in the universe, there's interaction between each of them, each pair. So that is the first thing to note. So it's between pairs, and they're directly proportional to the masses, and inversely proportional to how far they are together, the square of the distance between them. So those are the 2 factors. Those are the 2 things you need to know in this class. The rest will be expanding on these 2 points that Isaac Newton got for us. The gravitational force, the force of gravity between always occurs between pairs of masses. And it is proportional to M1 times M2. And it is inversely proportional to the square of the distance between them. So the farther they are, the smaller the force of gravity. But the rate at which it's falling, it falls as R squared, not just R. This is very, very important. R squared. So to recap, the force of gravity between two pairs of particles, let's say, is proportional to M1 times M2, where M1 and M2 are the masses of those particles, divided by R squared, where R is the distance between those two particles. So, of course, if you want to write the equation out, like you know, if you take out the proportional something, we introduce a constant. That constant is constant G, which is the universal gravitational constant. So the full equation for force of gravity, which is all you really need to know. The rest of the class will be extending it and applying it. So please note this. The force of gravity, Fg, between a pair of masses, M1 and M2, is equal to G, that's a constant, times M1 times M2, divided by R squared. That is, F is equal to G, M1 times M2, divided by R squared. That is it. But that relationship is between point particles, between particles. So what about if you have extended particles, like a bulk particle? So what we have to do is to treat that bulk particle as a several points. And like I said earlier, we compute the force of gravity between each point and the other point, and we sum together. That's what we do. If you have a good computer, fast computer, you can do that. However, if the object is symmetrical, particularly if it is spherically symmetrical, like a sphere, then life is much easier because there's a compensation between the various sides of the sphere. And at the end of the day, what happens is that it seems as if all the mass of that object is concentrated at the center. So all you have to do is assume that the mass is at the center of that sphere. And then you use that relationship again, F equals to G, M1, M2, all over R squared. I repeat, F equals to G, that's the gravitational constant, M1, M2 over R squared. Let's find out if you are following me. I hope you're following me. You have any questions? Any? Yeah? Okay. No, I press this. Okay. Exactly. We can okay, all right. I can see that you have written it very well. F equals to G, M1, M2 over R squared. Excellent. You've gotten it very, very, very well. Let me give you the attendance code right now. The first attendance code. The first attendance code is GW, that's the W as in water. GW, then U as in universe. GW, U, 9J. Code 1, GW, U, 9J. Okay, so my slides is now getting ready. We have to appreciate the technical people here. And again, I apologize for this. something. We'll be having the next class tomorrow. We thought we could finish tomorrow, but the way it's going, it might spill over to Monday, but we'll see how it goes. So you've gotten the most important point, that is the force of gravity between two masses M1 and M2 is equal to G, which is a constant, product of M1 and M2 divided by the square of the distance between them. So, and if it's an extended object, you will need, because that equation is between particles, the distance is well defined. But for an extended object, the distance is not quite so defined. So you have to take that object particle by particle, find the distances and apply that equation. If you have a fast computer, it's doable. But if you have an object that like it's a sphere, it's very straightforward because they will balance out the distances. There's a far one, there's a closer one. Everything will end up as if all the masses were centered at the center of the sphere. So you just look at the distance from the center of the sphere. That's the distance you will use. So if you have two spheres like that, for instance, the distance from the center of sphere 1 to the center of sphere 2, that is the R between the two objects. And then you have to square that. So the force of gravity between them will be G M1 M2 divided by R squared. Okay. The slide will be up very shortly. So I'm pausing. Let me see if can I take responses. Following you, sir. Thank you. We can't see the slides, sir. Yeah, the slide will come up shortly. This is physics. Yes, this is physics 101. Who is saying the slide? The slides are just coming up now. Please note the code. The first code is GWU 9J. You can see the slide now. You can see it. Okay. Now you can see the slide. Okay. So what you have here is we are following largely Halide and Resnick as before. Okay, excellent. Okay, please leave it. All right. Okay, so what we are doing right now is we are looking at this, because this is a real issue. Newton's law of gravitation. Let's move. So we've said this already. One thing with gravitational force is it's always attractive. It's always attractive. They attract things together. Unlike the electromagnetic force, which you will learn in physics 102, which depends on the type of charge. We have only one type of mass. One type, so it's always attractive. So it holds things together. And you can see the various applications. So at large distances, this is very, very important. Black holes, galaxies, apple falling to the ground, and so on and so forth. Planet, satellites, all these communicating satellites going around the planet, everything is held together by gravitational force. So I've said this already. And yeah, the force is between two objects. So let me make this point again. It's attractive between between particles, between a pair. So it's a kind of action-reaction force. So the force attracts M1 to M2, and it is the same force. However, the acceleration that will be experienced by the masses, of course, depend on the size of the mass, the magnitude of the mass. Because if you have the same force F acting on mass M1, the acceleration it will get is A1. So F is M1, A1. The same force acting on mass M2 will produce a different mass, a different acceleration, because it is F all over M2. I hope you can see that. So the objects they are experiencing the same force, but they will display this different acceleration, because acceleration depends on their mass. So when if the apple is removed from the tree, the restraining force that is keeping the apple on the tree, when it goes off, when the apple ripens. So there's no force keeping it on the tree again. So the force of gravity will bring it towards the earth. At the same time, that same force is bringing the earth towards the apple, because the same force. The amount of that force is G, mass of apple, times mass of earth, all over distance between the center of the apple to the center of the earth. That's the R. So that R squared. So the force between both of them is G, mass of apple, mass of earth, M, big M, divided by the distance between the two of them squared. So this same force will produce different accelerations in the apple and on the earth because of their sizes. So whereas the apple will experience a very, very big acceleration, the earth will experience virtually nothing. By the way, the G is 10 to the power minus 11 Newton meter squared per kilogram squared. So you can see that it's very, very small. So for a very big mass, you need big masses before this can be substantial, because before you can get 1 Newton. So this is the force, this is the equation we are talking about, and we are putting in vector notation. Now, the shear theorem is what I mentioned earlier. If you have a sphere, a spherically symmetric object, you can treat them as layers of spheres. So with this situation, it can be proved, you can check it online, you can see that the net gravitational force will the net mass will appear to be concentrated at the center here, at the center. So if it is uniform means you don't have it bulge, it's a sphere, and the masses are uniformly distributed in that sphere. You don't have a lump somewhere. So if you have this uniform spherical shear, so there are 2 points to note. Uniform means the mass is uniformly distributed, and then spherical means the shape is spherical. With those 2 conditions, it will be as if the entire mass were at the center. And in that situation, you can use the distance R that you are squaring will be from the center to the object that you are dealing with. Okay, I hope you got that. So this is the solving out that problem with the apple falling towards the earth. So it's an apple-earth accelerations. You can see based on what we said. Now let's move forward. The principle of superpositioning is essentially what I just said for an extended object. But for an extended object, for individual objects, I said force of gravity is between pair between two objects. If you have 1 million objects, each of those million objects will interact with the object of interest. So it's between pairs. And the net force on that particular object of interest will be the summation of the force of gravity due to all the others. So that's what you see in that equation 13.5. You sum together F on 1. M1, 1 is the object of interest. And there are many forces, many masses around it. So you just sum them together. So you move from I from 2 to N, where N is the number of masses available. So you do it for each pair, 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6, up to 1 and N. You now sum together. That's it. It's straightforward. So we call that principle of superposition. So the net force on the object of interest is the summation of the forces of all the other bodies nearby. But for a real extended object, you don't do summation, you do integration. And that's what I've just said earlier. And if that is spherically symmetrical, like a sphere, that integration will just give you the integration of a sphere, which will be for a sphere. For the surface area will be 4 pi r squared, the volume will be 4/3 pi r cubed. So I think, so this is what you have here. You have examples. This slide will be given to you by the course secretary with my voice embedded. So you can listen to this more at your convenience. And you see this. And of course, it's in Holiday. All this is taken from Holiday and Resnick. So you can also check. So this is just to, in this checkpoint, we have different masses. Please, how much time have I got, sir? Time. 12 minutes to go. Let me give you the second code, attendance code at this juncture. Second code is 5M as a monkey. 5M 4M as in monkey again. 5M 4M F. So 5 male, 4 male, female. 5M 4M F. Okay, in this example that we have checkpoint 2, we have 3 masses, 3 objects, 1, 2, 3, and we are looking at the net gravitational force on one of them. It's just a matter of using that equation by Isaac Newton, F equals to G M1 M2 all over R squared. So you do that F1 2, then you repeat it for F1 3, then you repeat for F1 4. You must do it vectorially. So in this situation, for instance, all of them are in the same axis. So just add. In this situation, you can see that the forces are different because one force is acting along this something, y-axis. This one is along x-axis. So actually you can, so the net force will be somewhere here, and so on and so forth. That's why you need your vector. So you can check it later on. So you have the answer there. Now, gravitation near Earth's surface. I hope I can treat this because and then we'll be done for today. Because the Earth, like you know, is, well, we call it a sphere. Let's assume it's a sphere. It's actually a geoid. It bulges at the center, like this, at the equator. But let's say it's a sphere. To find the force of gravity of an object, says this distance. This is the surface of the Earth. An object distance r from the surface of the Earth. What is the force of gravity between this object and the Earth? The mass of the Earth, we assume, is concentrated at the center. and the radius of the Earth is like 6,370 kilometers. So the distance between the object and the Earth will be not just r, but r plus re, the radius of the Earth. So it is this r plus re that you are going to square. And then m1, mass of the object, mass of the Earth, and of course g. So that's all. That's how it goes. So the r is the, so and you can see on the right, we use that formula for various altitudes. The altitude is the r, the small r, that's the height from the surface of the Earth. So that's the altitude. So you can see how it goes. And this, of course, the A, you can look at the acceleration due to gravity that is experienced at various altitudes. At kilometer 0, that is right on surface of the Earth. If you do the calculation, you know, the F is G, this F is G, M of the object, M of Earth, divided by R is plus R squared. That is clear. So from this, you can find the acceleration. This F is ma. So if you do that, you can see that the A will be just G, mass of the Earth, and R squared. So this R squared, we are changing it. When R squared is on the surface of the Earth, so this R is just the radius of the Earth directly. This is what you find, 9.83 meters per second squared. When this R is the altitude of 8.8 kilometers, and you add that to the radius of the Earth, you put it here. The answer you get for A will be 9.80. On Mount Everest, which is an altitude of 36, that's 8 kilometers. Everest is 8 kilometers. But for the space shuttles, you can see 38.8. You can see the acceleration of the gravity is falling. For a communication satellite, which is about 35 kilometers up in the sky, the acceleration due to gravity falls to 0.2. By the way, you can see this. This is why when you do Olympics, all those sports, you take into cognizance the elevation of where the event is happening. Because if you have it at a high altitude, the G is lower. G, if you have something happening at sea level, altitude of 0, the accelerated gravity is 9.83. Whereas at a high mountain, it can fall to 9.80. That can make a little difference in a 100 meters dash or high jump or vote jump. So you have to note this. So they have to correct the performance with respect to the altitude. So I think that's all we are doing is applying that simple formula. F is equal to G M1 M2 over R squared. That's all we are doing. And we are saying that for an object near the Earth, we look at the altitude, you add the altitude to the radius of the Earth. That's what gives that R beneath. And you apply this, if you go to the moon, for instance, on the moon, the mass of the moon is same for the mass of the Earth. So the same object will have a different acceleration ag, because in this equation, the m here will be mass of the moon, which is smaller. So the acceleration, or consequently the weight of the object, will be less. So the weight of object, which is the acceleration they feel with respect to gravity, depends on the bodies. I hope you got that. But everything is still applying that same formula. Force is G M1 M2 over R squared. Depending on the planet, depending on whatever, it's as simple as that. So, let me give you the last code now, because we have about 5 minutes or so to go. The last code 3 is U V, that's in ultraviolet, U V K. as in kindergarten, UVK G9. G as in Ganiyu. So the code 3 is UVK G9. And you can submit now so that you have time. Please submit the code now. Now, as I conclude this class, there are some modifications that come in. You can say complication if you want. Because the real weight that you experience may not be that AG that we are describing. The AG is simply following the formula. F is G M1 M2 over R squared, and the AG is divide that F by your M. So straightforward. But there are, for example, concerning the R, there are 3 reasons why you may not get that exact something. So note this. The first reason is that the earth mass is not uniformly distributed. So it's not a uniform sphere. You have some sea, hills, stones. So it's not uniformly distributed. So depending on where you are talking about, mountain ranges, whatever. Number 2, the earth is not a perfect sphere. It's a geoid. It bulges like this at the equator. So the distance to the center is not the same thing. Distance to the pole here is not distance to the center at the equator. The distance here is larger. So that will affect obviously the result you get. Also importantly, the earth rotates. It rotates on this axis. It rotates like this. And that rotation affects, because I need to explain that. Let me just explain that. The rotation is, if you have a body like this, but the rotation is easier to see from the equator. So an object on the equator on a rotating earth is moving in a circle. For something to remain on a circle, there's a force. We call that center seeking. There's a force to the center. So at the end of the day, it's as if it's diluting the gravity. The force of gravity is due simply between the masses, depending on the masses and the distance between them. But because it's rotating, that is modifying that. It's rotating in the circle. So it's this equation. This is what you measure. If so say you have a scale, this is what you calculated, what it should be. But because this is actually due to m v squared over r. This is the distance if something moving in a circle. This force. So the acceleration, if you write this out, will be m. This v will be what? R squared omega squared over r. So if you do that, you get this. So at the end of the day, the force of gravity, is mediated, is 3 factors. So my time is up. I will be stopping now. But just look at that equation. What causes weightlessness? If you can get something to move around, and with this something, you can get this equation to be 0. It's as if the guy has no weight at all. We will pick up from here tomorrow. Thank you. Okay. Sorry to stress you. One.
Yes. Yeah. Sure. Good morning, class. This morning we'll continue with fluid at rest. Fluid at rest. That's why we call it hydrostatic. 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 For us to look at two scenarios for which the fluid will be at rest, we look at the case of a diver going into a pool of water, diver in the sea. We know that the pressure increases with depth below the air-water interface. That is, the water will increase, with depth. And of course, if we are looking at a mountaineer also, we know that the pressure decreases with altitude. That explains why high-flying jets, you see the people that are there, the pilots, they will have headgear fitted with oxygen to actually keep up with the reduced pressure. So the pressure encountered by the diver and the mountaineer are usually called hydrostatic pressure because they are due to fluids that are at rest. They are due to fluids that are at rest. And then, of course, we want to look at how we can get an expression for hydrostatic pressure, which is a function of depth or altitude from the diagram. If you look at this diagram, just trying to show a liquid, presumably water, in a container. You see that the free force balance diagram is by the right-hand side. After the four diagrams, you can see we have three forces that are of interest. The force down the liquid and the force due to liquid that's pushing up F1, another one F2, and then the weight of the sample is also of consideration. You can see the free body diagram for the water in the cylinder. The gravitational force on the water from M, the mass of the water in the cylinder, as you can see in the figure, so that we can write the balance of these forces written as F2, because that's upward forces should be equals to downward forces. So we can write F2 equals F1 then plus the weight. So if we express that in terms of pressure, that equation in terms of pressure, that is F1 in terms of pressure, we just have F1 that is using pressure being force over area. So we can write F1 pressure product, okay, pressure times the area, then F2 likewise. So that if we put that in that formal equation, so we just have the product of pressure and area of F2 and that of P1A, that's for F1, because in this case, the area is the same. Then, of course, the weight, and that weight we can write, that's M. M we can write in terms of H rho G, something like the height, then with the area also. So that invariably we can say that A is common so that we can have pressure being equals to that, and in that form. So if you substitute these assumptions, we can see that pressure at a particular depth is just, or the total pressure is just the atmospheric pressure and then the pressure at that depth H. So that for that diver at a particular depth, the total pressure on him will include that of the atmosphere together with the pressure at that depth H. So, and this brings us to this very important conclusion. The pressure at a point in a fluid in static equilibrium depends on the depth of that point, but not on any horizontal dimension of the fluid or its container. That is just the depth, but not horizontal dimension. And then we should note also that the difference between an absolute pressure and an atmospheric pressure is called the gauge pressure. So use gauge to measure this pressure difference. And so we can have that expression, which is given by that. So if you look at this sample problem, you'll see that if you have a diver, if you see the expression, that is a diver practicing in a swimming pool who has taken enough air from his tank to fully expand his lungs before abandoning the tank at depth L, swimming to the surface, failing to exhale during his ascent. At the surface, the pressure difference, or what we call the gauge pressure, that is the difference between the external pressure on him and the air pressure in his lungs, is 9.3 kilopascal. So we want to know what depth does he start? And then, of course, to ascertain the lethal danger faced by such a diver. So we have introduced another thing, talking about pressure and gauge pressure. If you look at that expression, that the first one you see on this slide, if you take that pressure to the other side, so we're talking of pressure difference. And that is the difference between absolute pressure and atmospheric pressure. And that's what we call the gauge pressure. So we want to see how we can apply that to solving this problem. So you can see that in that solution on your right-hand side, the change in pressure is just P minus P naught, and density, the gravitation, and then the length. So it's that length you want to actually get, or what you call the depth. So you can see that the depth is at 0.95 meters. Okay? For that diver to experience 9.3 kilopascal. So, and of course, he has not gone deep at all. Not up to a meter. He has not gone deep. But he has to ascend. And the gauge difference is 9.3, which is just 9% of atmospheric pressure. Because you know that atmospheric pressure in Pascal is about 1.03 times 10 raised to 5 Pascal. Or let's say 100,000 Pascal. So if you look at 9.3 kilopascal or 9,300 Pascal. So it just actually 9% to rupture the diver's lungs and force air from them into the depressurized blood. And so it allows the pressure in his lung to equalize with external pressure, and then there will be no danger. Let's look at a U-tube system. And on one side, that's another sample problem. On one side, we have oil. On the other side, we have water.
two liquids in static equilibrium by way of illustration. So if you know the density of water, just about 1,000 on the right arm, and then oil of unknown density on the left. And the length is just 135 millimeter, and D, that is the difference between the heights. Be checking here, the length of water column, and then the height between the water column and the height of the oil column is 12.3. So if you add it to this, that will give you the total length of the oil column. So we want to know what's the density of the oil. So by way of approach, all these sample problems, there are questions, there are things you should know. Also want to apply the gauge pressure in this case, so that P, the pressure, and that of on the right arm, and then that of the left arm. So if you look at the two, the internal pressure actually should be the same. So if you equate them, that is on the right arm, the gauge pressure, when I say gauge pressure, I'm making reference to the pressure difference between that of the atmosphere and the absolute pressure. So we apply it to the right arm and also to the left arm. So as we have done that, we will see that if you equate the two, we'll have density difference of what we can express by what we have on that right-hand side. So that the density is 915 kilogram per meter cube. Okay, so we can see that in this approach, we do not need the atmospheric pressure to solve the problem. Because if you check on your left-hand side and you introduce what we call the gauge pressure, which is the pressure of the system minus the atmospheric pressure, it will just give you rho, G, and L. So rho, G, and L, if you equate the two, you'll be able to get this expression and get the answer easily. So, measuring pressure. For us to measure pressure, we use barometer, and we use the one we call the mercury barometer. And so we use it to measure the pressure of the atmosphere. And so it is as what we have here. Just have a tube, and then you have a basin, and in that basin you have mercury, and you are going to also have mercury also in that tube. So, and you try to now turn the tube and place it in the basin. So when you invert this, so there will be a column. There is a column, and that space actually has mercury vapor. In that space, have mercury vapor. And then we also note there are two levels. The lower level, which is the level of mercury in that basin, and then the level 2, which is also the level by which the mercury you have in the tube has dropped. So these are very, very important. So we have two diagrams. We have A and B. In A, the simplified version, then B, the other version. So, but H, in both cases, they are the same. And so it's still the same. And we can go ahead to look at, we can find the atmospheric pressure P naught in terms of the height, okay, of the mercury column. So that if we make our substitution, so we find that P naught is just rho GH, what we are used to. So for a given pressure, the height H of the mercury column does not depend on the cross-sectional area Please take note of that. For a given pressure, in the two figures, you see, this tube has a very thin width, but if you look at this one, it's bigger. But the column and the height is still the same. So this conclusion is very important, very vital. For a given pressure, the height h of the mercury column does not depend on the cross-sectional area of the vertical tube. Please take note of that. So the fanciful mercury barometer of Fig B gives the same reading as that of Fig A. All that counts is the vertical distance h between the mercury levels. So we can see that from the equation, that for a given pressure, the height of the column of mercury depends on the value of G at the location of the barometer. We all know that G varies on the surface of the Earth. G can be 9.8 meters per second squared. It can be 9.7 at the poles, 9.71 meters per second squared. So the height of the column actually depends on the value of G at the location of the barometer and on the density of mercury, which varies with temperature. Okay? The height of the column in millimeters is numerically equal to the pressure only if the barometer is at a place where G has its accepted standard value of 9.0 meters per second squared, and the temperature of the mercury is 0 degrees C. Let's look at another system that measures gauge pressure, maybe of a gas. If you look at what we have here, it's like a U-tube also. A liquid, you have a liquid with one end of the tube connected to the vessel, whose gauge pressure we wish to measure, and the other end open to the atmosphere. You can see. So this is an open tube manometer, okay, which we use to measure the gauge pressure of a gas. So we can find the gauge pressure in terms of the height shown. We already know the height between the two levels. So in the U-tube arrangement, there are two levels. The lower level, and then the highest level that is open to the atmosphere. So we find the gauge pressure, and so we have an expression that gives that gauge pressure, that's the pressure difference. Remember again, gauge pressure is the pressure difference between the pressure of the system and that of the atmosphere. And that is equal to rho GH. And this leads us to what we call overpressure. So if in inflated tires or the human circulatory system, if the absolute pressure, still talking about the gauge pressure now, if it's a case for which the absolute pressure is greater than the atmospheric pressure, we say the gauge pressure is a positive quantity. And so we can have what we call overpressure. Overpressure. So it can be positive and it can be negative. Okay? So when you squeeze one end of a tube to get, just an illustration again, to get toothpaste out at the other end. If you look at your toothpaste, you squeeze it on one end so that you want to get it. So what you are doing is you have changed pressure. That is, pressure is being moved from one end to the other, and that will push out the content. So that's the Pascal principle actually. So we say the principle, a change in pressure applied to an enclosed incompressible fluid is transmitted. So Pascal principle is talking about transmission of pressure. And that pressure is transmitted undiminished to every portion of the fluid and to the wall of its container. Okay? And we can demonstrate that pressure, that principle by looking at this system here. You can see there's a pressure. If you have a lead shot, you know lead shots are very heavy. And then you have a liquid and you try to compress it. So if you have a cylinder, by way of illustration, demonstrating Pascal principle, consider the case in which the incompressible fluid is a liquid containing a tall cylinder, as we have in this figure. The cylinder is fitted with a piston, that is something there to have, act as a lead, so that the liquid is contained. So the cylinder is fitted with a piston on which a container of lead shot rests. Like I told you, lead shots, they are very heavy. So if you put it, what happens? The atmosphere, the container, and the shot exert pressure, that's external pressure in this case, on the piston and invariably on the liquid. So that the pressure at any point P in the liquid, what will it be? It will be the external pressure and pressure due to high difference H. We are taking a point, say P, inside the liquid. You can see the point P inside the liquid. So we are saying the total pressure will be the external pressure and then the pressure due to this point. This typically shows what somebody inside a pool will experience actually. Imagine a diver that can go down. So the total pressure on that diver is the pressure due to depth and also the pressure due to the atmosphere. This is just illustrating that experimentally without going into the pool of water. This is just trying to show that. So what we are saying is, if you add a little more shot to the container to increase P external by an amount, change in external, the gate pressure is given by that. This pressure change is independent of H. So it must hold for all points within the liquid, as Pascal principle states. So we see how that principle is applicable in the case of hydraulic lever. This is what we are used to before now. For those of us that have done physics, whether at O level and all that, we've seen this figure before. Hydraulic press, okay? Or what we call hydraulic lever. You have the liquid, can be any liquid, can be oil, and then you have your input. The area for your input is very small, whereas the area for your output is bigger, because that's the area you want to use to carry a bigger load. So you have the force applied, smaller force, over that area to bring up a bigger force over a bigger area. So this is a good typical figure to show how Pascal principle can be made the basis of hydraulic lever. So if you have an external force magnitude Fi directed downward on the left hand, on our input side, whose surface area is Ai on your left side. We assume that the liquid is incompressible, which produces an upward force of magnitude F0 on the right hand, whose surface area is A0. If you must keep the system in equilibrium, there must be a downward force of magnitude F0 on the output from an external load, because though we didn't show that now. And if you look at there are some jack systems that are like this. So with a hydraulic lever, what we are saying is the change in pressure translates to ratio of the areas, ratio of the force to the area at both points, ratio of the force to the area at both points. That is, the pressure difference is the same. Okay? So that we can express the force over the area at one point of the lever the input point to the pressure to the force per area on the output point. So where we have used I for input in our indices for F and A, I for input and O for output. This equation shows that the output force on the load must be greater than the input force. I mean, this is purely mathematics. Okay? This is purely mathematics. Output force must be greater than the input force if there's a conditional thing. A1, A0, that's A output, is greater than A input. If we move the piston downward, if you move it downward, we know the area of the piston. So if you move it downward, moving downward means it will cover a distance. So that distance times the area gives you the volume. Okay? So the same volume that you are able to move there should be the volume you move over there. So we can also say, in addition to gauge pressure being force per area at one point, we can equally say the volume at one point also, that's another statement. The volume at a point, the volume of fluid move at a point should also be equal to the volume of fluid move at the other point. And so if you say that, so it's a constant. Just like gauge pressure is a constant, the volume is also a constant. And mind you, we have assumed an incompressible liquid so that we can actually know the distance, of output. And if we know the distance of output and the force of output, that brings us to what we call the work done or work output. And that work output can be expressed by the relation that we have there. So we have introduced three things now. Gauge pressure should be the same at the point of input and the point of output. We are also saying the volume of input should also be equal to the volume of fluid at the output. So if we have that, then the work done or the work output is the force of output and the distance as we have in output. And then if you introduce that, it should also be the work input. Very interesting. We show that the work done on the input piston by the apply force is equal to the work done by the output piston in lifting the load placed on it. So with a hydraulic lever, a given force applied over a given distance can be transformed to a greater force applied over a small distance. It's a statement that we must know. It's a very valid statement that we must know. That is, for a hydraulic lever, a given force applied over a given distance can be transformed to a greater force applied over a small distance. So three things we're able to get from this demonstration of Pascal principle. We're able to show experimental version, and then we're able to consider the hydraulic lever, and then we're able to establish that the gauge pressure is the same at one point of the hydraulic lever and at the other points of the hydraulic lever. Since you know pressure is force per area, so invariably, we are saying the force applied here over its area should be equal to the force applied there over its area. And then we can express force and area being, expressed as we have in that equation. Also the volume, because that piston actually moves down. That piston has an area and it moves down. So the area moved down with the height give us the volume. And we're also saying that the volume transmitted from the input area should also be equal to the volume transmitted in the output area. And we're also able to establish that the work output is also equal to the work input. So this takes us to Archimedes' principle. Please, do you have any question? Any question? Any question, please? Yeah. Any question? I'm trying to look at. Oh, okay. Sorry. Let's take our attendance. We should actually take our attendance. Sorry, we should arrange for. You should take attendance, actually. I hope I'm having it. Yes, we are using Halliday and Resnick 10th edition. You have to focus on every topic. I'm trying to. Well, my email, let me give you my email if you want my email. This is Physics 103. Attendance. Attendance school. Okay. Okay, I'll check. I'm just looking at their question. This is Physics 103. You should take notes. I'm responding to some of your questions. Okay. Okay. What's the message? Okay. So let's take our attendance. The first code for attendance now. MD 825. MD 825. That's attendance code 1. I'm still taking your questions. This is Physics 103, behavior of matter. We are using Halliday and Resnick, the 10th edition. So I would strongly advise that you take time. There are questions there at the back of that chapter. Please take a look at some of those questions. Very, very important. Take a look at those questions. Very, very important. Then my email address. Let me give you my email address. E-R-E-B, that's E for Emmanuel. E-R-E-B at oauife.edu.ng. E-R-E-B at oauife.edu.ng. More scroll to know the questions they're asking. Yes. It's not okay. So let's take the second attendance code. Our time is fast spent. Second attendance code. Let's take the second attendance code. L7D G8. L7 That's capital L. 7, capital D, capital G, 8. So we have taken 2 attendance. This topic is on density and pressure, and we are looking at fluids. Please, if you have questions, please ask your questions. And just like I said, for my own section, I strongly recommend that all the notes given, all the highlighted notes, please take note of them. You know, in trying to solve or to give question, if I were to set 10 questions, actually, you can be sure that minimum 4 of them will be theoretical questions. Question talking about understanding of the principles, word problems. And then 6 of such 10 questions can be calculations. I hope you understand what I'm saying. Hope you understand what I'm saying. That is, if one is to set 10 questions, you can be sure 4 of them will be word problems. 4 will be word problems. You can be sure of my own part. That's what I would do. Minimum will be 4. It can even be more. So I'm trying to lay or to let you know that you should take cognizance of the notes and the salient points that are raised in the notes, in addition to the calculation that may be relevant. And for the calculation, I told you, take time. At the back of that chapter 14 of Faraday and Resnick, which is what we are covering, at the back of that chapter, there are many questions there, more than 90 questions. You can be sure I will pick nothing less than 20 or 30. Not less than 20 or even 30 questions. So, somebody said, what type of calculations can be given about Archimedes' principle? We are here to look at Archimedes' principle. We'll look at it. We'll see how it is applicable. Okay, I can see your question. Somebody said, can we get the topics? Okay. I think the note will be online. The note will be online. So you can get the note online. But if I were you, I will listen carefully to what I'm saying or to what you are hearing from me. So listen carefully, not just the note alone. You're being able to listen. Also, we have value. We have value, good opportunity to understand the areas of interest. Very, very important. Then the third code. Let's take the third code. The third code. P, that's capital P. All of them capital, actually. P for R, G, 2. Let me take that again. P for RG2. P for Rg2. P4 Rg2. The Gmail, okay, I call it Gmail address. No, it's the university address I gave you. For somebody, for your, in case you want to contact me, in case you want to contact me, in case you want to send me a mail, I prefer a mail than giving my number. Okay? I prefer you sending me a mail than giving my number. And that's why I gave you the email address. And the address again is erib@oauife.edu.ng. erib@oauife.edu.ng. I'm still looking at your question. It is nice for me to take questions and to know. So you can get the slide. The slide will be online. The slide will be online. In fact, the YouTube, as I was made to understand, will also be online. The YouTube will also be online. Okay. So you can also get it on YouTube. Akibolu, the Ayola, the something is starting with the code is P, not B. P for Peter. P for RG2. P for RG2. Akibolu Ayola, please take notes. It is P, starting with P, not B. It's starting with P. P for RG2. Okay, so let me just state the Archimedes principle without, we'll not go into it. So we'll be stopping there actually, but I'll just, we know it before now. Talking about when the body is fully or partially submerged in a fluid, we call it a buoyant force. But what we normally call it before now, we call it the upthrust. You remember? During your own level, we say, okay, upthrust. You know, it's a force. Whether we call it upthrust or we call it buoyant force. Okay? But let's state it the way it is here. When a body is fully or partially submerged in a fluid, a buoyant force from the surrounding fluid acts on the body. This force is directed upward and has a magnitude equal to the weight mg. Remove that F. There's no F there. Or it should be a subscript of the fluid that has been displaced by the body. And that explains why ships, as massive as they are, can actually float in water. Whereas a needle, as tiny as it is, will be submerged. Very interesting. That is, the ship will actually displace weight of the fluid in which it is submerged, in this case water. The weight of water displaced will be equal to its weight. So you can see that some massive ship, super tanker or ocean liner, as massive as they are, or aircraft carrier, as massive as they are able to displace enough fluid, enough water equal to their weight. And that is the reason why such ocean liner or ship cannot pass through many ocean. That is, and cannot even dock at some seaports. If the seaport is not deep enough, bigger ships cannot anchor there because they won't have volume of water enough because of the shallow area of the docking area. They won't have enough water to displace that will be equal to their weight. And so in Nigeria these days, we talk of deep sea ports, or what we call the Lekki deep sea port. That is, to a particular depth that can allow bigger ships to actually anchor and offload its contents. So it is very important to note this because of what we call Archimedes' principle. That is, enough fluid that will be equal to the weight of the body that is submerged. So that's the Archimedes principle. And of course, the expression. The buoyant force is just M of the fluid, and G. MF is the mass of the fluid that is displaced by the body. Please let me see if there are questions. I'm rounding up. Somebody is asking for the second code. Let me check the second code. Second code, L7 DG8. L7 DG8. Somebody said, can work done equals mass times gravity? Mass and gravity is what? Mass times gravity is what? That's force or weight. And work is force times distance. And I've stated earlier, the slides will be available online. The last code starts with P. P for Peter. So any other question as we round up for the day? Yes, there is a way to get the online. Online. In your link, I was told you check the archive.
Yes, sir.
Check your link for any information about this lecture. Check your link. I was told you have a link. I was told you should have a link. And from that link, you can get it. And then the very first thing you can also check in trying to search for this lecture, check TELEPRESENCE, ACE, OAU. I think that's a very good thing to start your check from. TELEPRESENCE, OAU. If you type it on Google, it will bring you many things. See if there's any link to lectures, and from such link to lectures, check Physics 103 lectures. Yes, you have to use Halliday and Resnick. And like I told you, please, in that Halliday and Resnick, go and check the questions in chapter 14. There are many questions in that chapter 14. Avail yourself the opportunity to solve some of the questions. I've not said all. Some of the questions there. And I told you, the questions there, they are close to 90, if not above 90. And you can be sure your questions will be drawn from among the 90 questions, and more than 20 of your questions will be there. So take opportunity to look at that Halliday, the 10th edition. So our time is up. I hope to meet you by God's grace on Friday for the continuation of our topic. I will be looking at Archimedes' principle. Thank you very much. God bless.
Thank you very, very much. So,